Hello, my name is Sarah Kulak, and I'm here to talk to you about the fascinating world of thermodynamics. So, thermodynamics is a science that talks about heat and energy and the relationship it has to each other. Thermodynamics can be hard to understand, so I'm going to use some real life examples later to make it easier for you. So, thermodynamics has three laws, and the first law is known as the law of the conservation of energy. And what this law says is that energy cannot be created or destroyed, only transferred or changed from one point to another. It's like the love our parents have for us and our siblings. They do not create their love, it just happens. They cannot destroy their love. Their love just exists, but it can be transferred and shared between us and other family members without being removed altogether. We're doing work on our body, we gain heat and it gives us more energy. And when we lose heat or we are doing work on something else, we have less energy. And so, like, for example, when you're playing tag and sweat's pouring down your face and you get really tired, it's because you're running and you're doing work and you're using all that energy and you're getting all of it out and you're releasing heat, so your energy is decreasing. The second law of thermodynamics says that the entropy of an isolated system is always increasing. This means the amount of energy that cannot be used for work is increasing because the part of the energy used in a system is being used for heat, which requires energy. Entropy increases disorder, and the best way to show this is when a room gets messy, it will result in even more disorder until it gets cleaned up. But the energy that is used to clean the one room will decrease the energy you can use to clean the other rooms, resulting in the mess in the other rooms as well. So the next thing we're going to talk about is Gibbs free energy and spontaneity. Gibbs free energy is the amount of energy that can be used for doing work. So there are two types of chemical reactions: exergonic reactions, which release heat, and endergonic reactions, which take in heat. Now these are important to remember when we discuss spontaneity. Spontaneity is split into two parts. Something is spontaneous if it's a natural process that needs no energy to start. It is non-spontaneous if it needs energy to start the reaction. So when you are sledding, going downhill is spontaneous because you don't need energy to start. The incline just makes you go down. However, when you trek back up, you need to put energy into the sled, pushing it up the hill. So it is a non-spontaneous reaction. Also, sledding down a hill releases energy, so it is an exergonic reaction. And pushing up a hill requires the absorption of energy, so it is an endergonic reaction. We use the Gibbs free energy equation to figure out how much Gibbs free energy we have. The G in the equation represents Gibbs free energy, the S represents the entropy, the T is the temperature, and the H is the total energy of the system. So to sum it up, in exergonic reactions, heat is released. Therefore, the Gibbs free energy in the system is negative. This is also a spontaneous reaction. In endergonic reactions, or non-spontaneous reactions, energy is absorbed, so the Gibbs free energy is positive. So now we're going to talk about activation energy. And activation energy is like the match that starts the fire. All chemical reactions need activation energy, no matter if they're exergonic or endergonic. Activation energy comes from heat energy of the surrounding system, and once the system has absorbed enough heat energy, it will move on to a transition state and start the reaction. The more activation a reaction has, the longer it will take to react. It's like a wagon. The more stuff you put on it, the longer it will take to move. A lot of times, to increase the speed of reactions, catalysts are used to decrease the activation energy because the activation energy in cells is too high, and if it is too high, the cells could just totally disintegrate. So in the picture above, you see an enzyme working as a catalyst. Without the enzyme, the activation energy is way too high, but with the enzyme, the activation energy is much more reasonable. In order to protect cells and store energy, our body uses something called ATP, or adenosine triphosphate, which is made up of AMP, adenosine monophosphate, and two phosphate groups. The phosphate groups are negative so that the ATP is unstable. And ATP is broken down in water in hydrolysis, separating the ADP and phosphate group in a process known as dephosphorylation. And this releases energy that we can use for heat or energy for work when we need it. So during dephosphorylation, we are opening a present, and when we open it, we get the benefit of either more energy or heat. The phosphate group that is released during this process is added on to another ADP and creating an endless cycle between the breakdown and creation of ATP. This is an example of an energy coupling reaction where an exergonic reaction that releases energy drives an endergonic reaction that requires energy. This is known as energy coupling. So our last topic is equilibrium. So basically, we never want to reach equilibrium because nothing is changing and we're not alive. Living organisms can never reach equilibrium because we're at an open system, so things are constantly moving in and out of our bodies, and we can never reach equilibrium this way. If we are not at equilibrium, we always have energy to do work. So when we have more energy, we are farther away from reaching equilibrium. Hydrolysis breaks down ATP into ADP and phosphate groups in exergonic reaction. The exergonic reaction is then coupled with the endergonic reaction through the transfer of a phosphate group. The transfer of a phosphate group makes the molecules more reactive. And when the instability of the reaction occurs, the speed is increased on the side of the reactants, creating disequilibrium. Because of the energy coupling, the products of the reactants become more stable than the reactants, thus the equilibrium is not reached. Equilibrium is like a seesaw. We never want the seesaw to be perfectly straight. We always want the seesaw to be on one side. And that is all we are going to do on thermodynamics. I hope that helps clarify it for you.